The next question says, a rigid sphere is held at rest on the seabed. When the sphere is released, it rises to the surface of the seawater. The seawater has uniform density. Which statement about the sphere from its release until it reaches the surface is correct? So we have to work by elimination here. The sphere always moves with constant acceleration. Now, this is debatable. Why is it debatable? Uh, because constant acceleration, then it means that there is a constant resultant force. Now, we know that as it is moving, as it is released, then it starts to move. Its speed at first is increasing. For whatever reason, it is increasing. This would increase the drag forces. So the forces on the sphere are definitely not constant. So even basing upon that, even though the drag force will ultimately start to decrease, basing on the fact that the drag force was increasing at first, because drag force depends on the speed. If speed is increasing at first when it is released, then definitely the drag force was increasing also, which would mean that we had an increasing drag force, then the resultant force was not a constant, and acceleration cannot be a constant. Then the next one says, B says the sphere is always moves with a constant velocity. As I said, for it, if it is released from rest, then there's no chance that it is always moving with constant velocity. Then the magnitude of the speed is always to be a constant from start, which doesn't make sense considering that it is released from rest. The original speed is zero, so the speed, if it's zero, then it changes to another speed, then it is not always moving with a constant speed. Whatever happens, even if it changes to a speed of 2, which then becomes constant, there is a movement from the speed of 0 until the speed becomes 2. So that alone means that the velocity is not always constant. Then the other one is saying the upthrust on the sphere always decreases. But here's the thing now. The upthrust, formula for upthrust says upthrust is equals to the density of the liquid, the gravitational field strength, volume of the liquid displaced. Now, as long as the sphere is inside the water, as it is rising, but as long as it is still inside the water, then it can be clear that the volume that is displaced, since it will be displacing a constant volume, it is clear that the upthrust will always be constant as long as the sphere is inside the seawater. And remember, this is being done from its release until it reaches the surface. The moment it reaches the surface, then we stop. So the expectation is that as long as it was inside, then the volume displaced was a constant. Density of the liquid was also said to be constant or uniform there. So upthrust is also a constant. So upthrust is always a constant. Upthrust does not decrease. The next question, which was a problem, was this one. An escalator is 60 meters long and lifts passengers through a vertical height of 30 meters. So as you can see, this is the 30 meters that they're talking about. Lifts passengers through a height of 30 meters there. To drive the escalator against the force of friction when there are no passengers requires 2 kilowatts. So if there are no passengers, if we want to drive the escalator just against the forces of friction, meaning that there are forces of friction which are opposing its movement. So if we want to overcome those forces of friction, so in other words, it is talking about the power needed to overcome the forces of friction, just overcoming the forces of friction without us lifting passengers, without giving passengers a gravitational potential energy. The goal just being overcoming the frictional forces. If the goal is overcoming the frictional forces, then it means that the power being lost to frictional forces is the one that we are supplying. So when we are supplying 2 kilowatts just to overcome frictional forces, then it means that the frictional forces are taking away a power of 2 kilowatts. It's like, for example, if you're paying for a service and if you have to earn, let's say, $1,000 a month, just so that you can pay all your expenses and be left with nothing. But if the goal is just so that to pay the expenses, you need $1,000, it means that the expenses themselves are $1,000 because you must earn $1,000. So the same thing is what is being said here. The escalator is used by passengers of average mass 60 kgs, and the power to overcome friction remains the same. So the power that is lost to friction is not going to change when now we are lifting passengers. The power that is lost, the power that is used to overcome friction, or the power that is converted by frictional forces to heat, is not changing. It's 2 kilowatts, even when we are lifting passengers. How much power is required to drive the escalator when it is carrying 20 passengers and is traveling at 0.75 meters per second? Now we have to be very careful here. When it is traveling at 0.75 meters per second, the question becomes, why should we be worried? We want to know the power that is required to drive this escalator. So to know the power that is required to drive this escalator, we need to know, since we already know that it requires another extra power of 2 kilowatts, we need to know the extra power needed to lift these passengers. Power, remember, is energy per unit time. So these passengers, remember, they are gaining gravitational potential energy as you're lifting them. So we want to know the amount of gravitational potential energy gained per unit time. So for each passenger, we can agree that the gained gravitational potential energy, which would be mgh, is simple. The passenger is 60 kgs, but there are 20 of them. So let's just say times 20 times 9.81 times the vertical height gained. So now we need to know the time so that we can find, by dividing the energy gained by the time taken, we will be able to know the power that was gained by the passengers. But the power that was gained by the passengers was supplied by the escalator. So the escalator is supplying 2 powers, one to the frictional forces and one which is then gained by the passengers. So we need the time it was gained. So the time it was gained, if the vertical height moved is 30, then the speed of the escalator is 0.75 for a distance of 60. So we could actually say that 0.75, that's the speed, the distance, we have it. So 0.75 into 60 now, that's more like, still I don't have a calculator, so it's more like 60 divided by 0.75, which then is more or less like dividing by 3/4, which is more like dividing by 3 and multiplying by 4, which is 20 times 4, which is 80. So it takes 80 seconds there. So this into this, that's 4. This into this, that's 15. Now it's 15 times 9.8 times 30. Okay, now I need a calculator. Just a moment. Okay, so we say that it's 15 times 9.81 times 30, then divided by, okay, it's already finished there. That's 4,414.5. Then if you divide that by 1,000, that's 4.4. That would be 4.4 kilowatts. So 4.4 kilowatts plus 2 kilowatts, that's 6.4 kilowatts. So that gives us 6.4, the answer that we got in B there. Then number 19. An object is stretched until it reaches the elastic limit. Which statement must describe the stress on the object when it is at the elastic limit? So we want to know the stress when it is on the elastic limit. It is the maximum stress. A is saying it is the maximum stress for which the object obeys Hooke's law. Now that is wrong now, because the elastic limit is not necessarily the final point where Hooke's law is obeyed. Hooke's law actually is obeyed until the limit of proportionality, which for the most part happens before the elastic limit. So when they say that it is the maximum stress for which the object obeys Hooke's law, the stress that it experiences at the elastic limit, then that is wrong. Then B says it is the maximum stress that can be applied to the object before it has elastic deformation. Now, at the elastic limit now, the elastic limit is the final point where elastic deformation ends, and then the commencement of plastic deformation begins. So when it says that before it has elastic deformation, it is wrong, because elastic deformation ends at the elastic limit from when the force was 0 to when we reach the elastic limit. That's where we have elastic deformation. Plastic deformation then commences after that. So B is wrong. Then C says it is the maximum stress that can be applied to the object before it has plastic deformation. Now that is correct. Then let's see why D is wrong. It is the maximum stress the object can withstand before it breaks. No. The stress an object has at the elastic limit is not the maximum stress before it breaks. Objects don't break at the elastic limit. Object don't break at the elastic limit. After the elastic limit, there is the yield point, there is plastic deformation, and then there is what we call the breaking stress. So all that comes after the elastic limit. So this is not the maximum stress. So answer is C.